Okay, there's one more thing I'd like to go over in the time domain unit, and it's a thing called Shepard tones, which is very cool, and it's going to be a tool that we can use later in Unit 3 to sonify some of the features that we're going to design to pick up on pitch. But for now, it's this cool effect, which, let me just play the sound for you first, that we're going to make, and then I want you to tell me, when does the sound stop going up? Okay? So let's play it. So, this nice little illusion here is a sound that sounds like it's always going up. And it never stops, and we can play it infinitely, and it'll keep sounding like that. Alright, so I want to look at this sound in a different way, and I'm going to use something called a spectrogram, which we're about to talk about in the next unit. But basically, it's going to try to estimate the frequency content in very small windows so we can see it changing over time. So if I go to play the sound that I just made, something very interesting happening, which is there are a bunch of frequencies going at the same time, and in fact they're all octaves of each other. So it's the same note, just at a bunch of different octaves. And what happens is, as the top octave gets high enough, we suddenly jump down and start to make that one of the lowest notes again. So we kind of hide this little change here of the top octave going down and making the lowest octave. So let me show you how to do this in code. So if I pop back here into the code, that's what we got to do. We got to make a bunch of octaves that keep going up, and then as soon as the highest one gets high enough, we wrap it around. So it's just like the Barber pole illusion, if you've ever seen that. So let me do that, and what I'll do is I'll define the instantaneous frequency for a bunch of different octaves of pure tones, and I'll add them all together. So let me first define the sample rate, and now let me define, I'll call it the base frequency. So I'll start this off pretty low. So this is going to be where, like, the lowest note that we have, it's going to start off at that note. And then I'll make it go up over time. Let me also set up the time here. So let me make 20 seconds of this. And the other thing that I've got to choose here is how quickly am I going to do this kind of wrapping around. So I'll call that maybe the octave rate. Maybe I'll say 0.2. So that's why I gave an example. So this is number of cycles of Shepard tone per second. So here I'm saying once every 5 seconds I want to repeat this thing. Okay, and then I'm going to wrap around, and then it's able to keep going, as I was showing here. Okay. All right, now what I got to do is let me set up an array that's all zeros, and I'm going to add a bunch of frequencies in here. And so let me choose how many octaves I want. And I got to be a little bit careful about this, because as we'll see in the next unit, we can't ever have a note whose frequency is above half the sample rate. Okay, so it turns out if I use 9 octaves, so right before I wrap around, I'll be at about the base frequency times 2 to the number of octaves. I'll be just below that. Okay, so that number is 15,360, which is below half the sample rate. So we're safe to go up that high. And so what I'll do is I'll loop through the octaves. And for each one, I'll create an instantaneous frequency trajectory. And so what that's going to be is, okay, it's going to be the base frequency times 2 raised to the ith power. Okay, so I'm gonna, the one at the bottom starts off with the base frequency. The one above that is going to be double that. The one above that is going to be quadruple that, so on and so forth. But actually, we need to also continue to go up in frequency. So what I'll do is I'll add on the time here. So as a function of time, I want to increase by this number of octaves per second. So if I say, let me add on t times the octave rate. And if I check this, it's like, okay, every 5 seconds, I'm going to increase by 1 octave. And that's pretty much what I want to do, except I want to wrap around. And so what I'm going to do here is I'm going to make this be modulus the number of octaves. So it's okay to keep increasing and going to the next octave, to the next octave, to the next octave. But if you get high enough, I want you actually to wrap around back to 0 again. Okay, so that's what this modulus here is going to do. So again, if you forgot what the modulus means, just remainder after dividing by this. So I'm never going to go up to 9 octaves fully. I'm going to get just about there, 9 octaves above, and then I'm going to wrap back around to 0, to the base frequency. Okay? So this is my instantaneous frequency. But I need to turn that into an actual pure tone. And as you recall, the way that we do that numerically is to do a cumulative sum. That's the simple rectangular integral. So I would say here f is equal to cumulative sum of this instantaneous frequency over the sample rate. That's because the width of the rectangles is 1 over the sample rate. So you can go back and review my other video on that. I could actually do this analytically too, but you won't really notice much of a difference. So I'll just do it numerically for now. So say integrate instantaneous frequency. And then finally, let me accumulate this pure tone. And so I'm going to add here 9 different tones together. And this is the tone that I want. So say y plus equals cosine of 2 pi f. All right? Good. So let me hear if I got it. Oh, actually, one more thing I should do. I don't want to hear, I kind of want to hide what's going on a little bit at the top, possibly. So let me divide the amplitude of this by I plus 1. It's just one little thing I could do, or maybe I could divide by I plus 1 squared or something. We can try a couple different versions. So here's divided by I plus 1. We divide by I plus 1 squared. Let's see here how different that is. So there, the bass is a lot stronger. I kind of like that one, actually. Okay, so let me, I'll leave you with this. There's a way to look at the spectrogram, and we're going to be doing this in the next unit. We're actually be computing this thing I showed you a moment ago. But I'll just leave you with this in the notebook to show you here. There's a library called Librosa that will do this for us. Although, again, we're going to do it ourselves from scratch. But let me just show you how to do this in Python. So if I were to say librosa.stfty, and then I said, okay, I'm going to look at this in decibels. Remember, we're actually sensitive to loudness and logarithmic scale. So there's a method in Librosa called amp2dB. And don't worry too much about this right now. We'll talk about that more later. And okay, so let me now say librosa.display.spec show. So Librosa has done some nice plotting things here. I want the x-axis to be in units of time. And I want the y-axis to be in linear units of frequency. I'll start off with. I want to give it the sample rate so it gets the scale right. And then this is going to show me the amplitude. Okay, so here it is. Here's my Shepard tone. So again, remember, since we're going up linearly in frequency, we actually end up going exponentially since we go up linearly in pitch, is what I was doing here. This is going up linearly in pitch. We end up going exponentially in frequency. That actually, leads to kind of squashed, like the first few frequencies get really squashed down here. So let me also show you a plot where this is logarithmic spacing, which is often how people look at spectrograms. So if I display the frequency on a log axis, you can see a little bit more clearly what's going on in the low frequencies here. And you can see that, yes, it's actually linear on a log scale. Okay. So there you have your Shepard tones. I hope you enjoy that. The code's pretty simple. And now we're finally ready to move on and start talking about, well, how do I create these kind of plots? That's what we'll do in the next unit. Actually, I realized there's one little mistake I made here. So I was trying to make it so that the high frequencies would be softer, and that's why I had the larger I dividing this. But eventually, the lower frequencies are going to turn into higher frequencies. So this really needs to be depending on somehow the note. I want kind of higher notes. So maybe I'll call this is really, or I guess I should say octave. This is where am I? What octave am I in? And so really, it should be like, instead of I down here, it should be octave, although there is a slight problem with doing this. Let me show you that. So now it doesn't depend on I, it's just going to be depending on what, instantaneous frequency I'm actually at for whatever tone I'm playing. Okay, yeah, so there's an issue here because this is, I have to divide by 0, so I'll say 1 plus octave. But that's actually not the only problem here. So if I do it like this, I get these clicks because what will happen is it gets softer and softer as the frequency gets higher. That's the way I have it set up here. But then suddenly that transitions to a much louder, lower frequency, so you'll hear these clicks. I'll show you real quick. Yeah, did you hear that click right there? So what I really should do is probably make it the loudest in the middle here. And I'll make it the same loudness at the two edges here so that I don't have that problem. So what I'll say here is, okay, denominator, I'm going to make that be, I'll say the absolute value of whatever octave I'm at minus the halfway point, which would be n octaves over 2, roughly. And so what I can do is divide by 1 plus that. And so I'll say, yeah. Or I guess I'll just make that be the denominator. So I'll say denominator is 1 plus that. Okay, so now I don't have that click. So if I play this. Okay, so that's a better Shepard tone because now before the ones that were lower frequencies were getting louder and louder. So this is a little bit more correct here. So I will leave you with that code and you can enjoy that.